Welcome to green chemistry, the design of chemical products and processes that reduce or eliminate the use and generation of hazardous substances. In this presentation, we will explore the 12 principles of green chemistry as formulated by Paul Anastas and John Warner in 1998. Learn how chemistry can be made inherently safer and more sustainable. Discover real-world applications from industry. Master key metrics like atom economy and E-factor through worked problems. And test your understanding with comprehensive quiz questions. Green chemistry is not just about cleaning up pollution. It is about designing pollution out of existence from the very start. Green chemistry emerged in the early 1990s from the convergence of pollution prevention programs, growing environmental awareness, and innovative chemical research. In 1991, the U.S. EPA launched its green chemistry program under the leadership of Dr. Paul Anastas. The term green chemistry was formally defined as the design of chemical products and processes that reduce or eliminate hazardous substances. Unlike environmental chemistry, which studies pollutants in nature, green chemistry intervenes at the design stage to prevent pollution from occurring at all. In 1998, Paul Anastas and John C. Warner published their landmark set of 12 principles that continue to guide the field today. These principles transformed how chemists think about synthesis, materials, energy, and waste, shifting the paradigm from end-of-pipe treatment to intrinsic molecular design for sustainability. The 12 principles of green chemistry provide a comprehensive framework for designing safer, more sustainable chemical processes. Principle 1. Prevention. It is better to prevent waste than to treat it after formation. Principle 2. Atom economy. Maximize incorporation of all starting materials into the final product. Principle 3. Less hazardous syntheses. Design methods that use and generate substances with little or no toxicity. Principle 4. Safer chemicals. Products should be fully effective yet non-toxic. Principle 5. Safer solvents. Minimize the use of auxiliary substances. Principle 6. Energy efficiency. Conduct reactions at ambient temperature and pressure whenever possible. Principle 7. Renewable feedstocks. Use renewable rather than depletable raw materials. Principle 8. Reduce derivatives. Minimize protecting groups and temporary modifications. Principle 9. Catalysis. Use catalytic reagents rather than stoichiometric ones. Principle 10. Design for degradation. Products should break down into innocuous substances after use. Principle 11. Real-time analysis. Develop methodologies for in-process monitoring to prevent pollution. Principle 12. Inherently safer chemistry. Choose substances that minimize the potential for accidents. Principle 1. Prevention. States that it is better to prevent waste than to treat or clean up waste after it has been created. This is the most fundamental principle. The ideal waste management strategy is not to produce waste at all. Principle 2. Atom economy, introduced by Barry Trost in 1991, measures how many atoms from the starting materials end up in the final desired product. A reaction with high atom economy incorporates most of the reactant atoms into the product, generating minimal byproducts. Atom economy is calculated as the molecular weight of the desired product divided by the sum of the molecular weights of all reactants, multiplied by 100%. For example, the traditional production of hydrazine via the Raschig process has poor atom economy because it generates stoichiometric sodium chloride waste. The greener peroxide process uses hydrogen peroxide as the oxidant with water as the only byproduct, achieving much higher atom economy. Principle 6 emphasizes that energy requirements should be minimized and reactions should be conducted at ambient temperature and pressure whenever possible. Energy-intensive processes contribute significantly to the environmental footprint of chemical manufacturing. Principle 7 advocates for the use of renewable feedstocks, raw materials derived from agricultural products, biomass, or waste streams, rather than depletable fossil fuels. Bio-based chemicals such as polylactic acid from cornstarch, biosuccinic acid from fermentation, and 1,3-propanediol from genetically engineered E. coli exemplify this principle. Renewable feedstocks reduce dependence on petroleum, lower net carbon emissions, and support a circular bioeconomy. However, careful life cycle assessment is necessary. Using biomass is not automatically greener if it requires excessive land, water, or energy for processing. Principle 9 states that catalytic reagents are superior to stoichiometric reagents. Catalysts are substances that increase reaction rate without being consumed, allowing a small amount to facilitate many reaction cycles. Catalysis reduces waste by eliminating the need for excess reagents, lowers energy requirements by providing alternative reaction pathways with lower activation energy, and enables more selective transformations with fewer byproducts. Both homogeneous catalysts dissolved in solution and heterogeneous catalysts on solid surfaces are widely used. Principle 8 advises minimizing the use of protecting groups and other temporary derivatives, which add synthetic steps and generate additional waste. The 2005 Nobel Prize in Chemistry was awarded for olefin metathesis, a catalytic method praised for its contribution to greener chemical synthesis. Enzyme catalysis and biocatalysis represent the ultimate in green catalytic technology, operating under mild conditions with exceptional selectivity. Principles 3, 4, 5, and 12 focus on safety at every level of chemical design. Principle 3 calls for synthetic methods that avoid using or generating substances toxic to humans or the environment. This requires chemists to consider the toxicity of every reagent, solvent, and byproduct from the earliest design stages. Principle 4 extends this to the final product itself. Chemical products should achieve their intended function while being as non-toxic as possible. Principle 5 addresses auxiliary substances like solvents, separation agents, and drying agents, which should be avoided or replaced with benign alternatives whenever practical. Green solvents include water, supercritical carbon dioxide, and bio-derived solvents like ethyl lactate and 2-methyl tetrahydrofuran. Principle 12, inherently safer chemistry, requires choosing substances and process conditions that minimize the risk of accidents, explosions, fires, and releases. The physical form of a chemical matters. Handling a solid is generally safer than handling a volatile, flammable liquid. Green chemistry has produced transformative industrial applications. Dow Chemical won the 1996 EPA award for using supercritical carbon dioxide as a blowing agent for polystyrene foam, eliminating ozone-depleting CFCs and flammable hydrocarbons. The production of ibuprofen was redesigned from a 6-step stoichiometric process with poor atom economy to a 3-step catalytic process, achieving 99% atom economy, a landmark achievement in pharmaceutical green chemistry. NatureWorks produces polylactic acid from cornstarch for biodegradable packaging, cutlery, and textiles. Novozymes and Archer Daniels Midland developed an enzymatic intrasterification process to eliminate trans fats from margarine and shortening. BioAmber produces succinic acid from renewable feedstocks through bacterial fermentation, sequestering carbon dioxide in the process. Shaw Industries created EcoWorks carpet tile backing using polyolefin resins that are fully recyclable and non-toxic. Quantitative metrics are essential for evaluating the greenness of chemical processes. Atom economy, proposed by Barry Trost, measures theoretical efficiency. The E factor, introduced by Roger Sheldon, measures the actual mass of waste per mass of product, the environmental impact factor. A high E factor indicates a wasteful process. Reaction mass efficiency compares the mass of product to the mass of all reactants used. Carbon efficiency measures the percentage of carbon in the reactants that ends up in the final product. Process mass intensity is the total mass of all materials used per mass of product, including solvents, water, and reagents. The ideal values are 100% atom economy, E factor of 0, 100% reaction mass efficiency, and 100% carbon efficiency. In the pharmaceutical industry, typical E factors range from 25 to over 100 kilograms waste per kilogram product, compared to the oil refining industry where E factors are near zero. Quiz question 1. Which principle states that it is better to prevent waste than to treat it after it has been created? Option A, atom economy. Option B, prevention. Option C, catalysis. Option D, design for degradation. Think carefully about your answer. Quiz question 2. What is the atom economy of a reaction where the molecular weight of the product is 120 grams per mole and the sum of the molecular weights of all reactants is 200 grams per mole? Option A, 50%. Option B, 60%. Option C, 75%. Option D, 80%. Apply the atom economy formula to calculate your answer. Quiz question 3. Which of the following is an example of a green solvent? Option A, benzene. Option B, carbon tetrachloride. Option C, supercritical carbon dioxide. Option D, diethyl ether. Remember what makes a solvent green? Quiz question 4. A company produces 100 kilograms of product and generates 2,500 kilograms of waste. What is the E factor? Option A, 2.5. Option B, 25. Option C, 0.04. Option D, 250. Remember, E factor is waste divided by product. Quiz question 5. Which green chemistry principle is best illustrated by enzymatic interesterification to replace chemical catalysts in fat processing? Option A, Principle 7, renewable feedstocks. Option B, Principle 9, catalysis. Option C, Principle 10, design for degradation. Option D, Principle 12, safer chemistry. Consider why enzymes are used in the first place. Problem 1. Atom economy of hydrazine production using the Raschig process. Calculate the atom economy for the traditional Raschig process for hydrazine production. The reaction is sodium hypochlorite plus 2 ammonia yields hydrazine plus sodium chloride plus water. Step 1. Identify the desired product. Hydrazine, N2H4, with molecular weight 32.05 grams per mole. Step 2. Sum the molecular weights of all reactants. NaOCl is 74.44 plus 2 times ammonia, which is 17.03 each. Step 3. The sum of reactant molecular weights equals 74.44 plus 34.06, giving 108.50 grams per mole. Step 4. Atom economy equals 32.05 divided by 108.50 times 100, giving 29.54%. Step 5. For comparison, the peroxide process using hydrogen peroxide as oxidant achieves an atom economy of 63.9%. Conclusion. The Raschig process wastes approximately 70% of reactant mass as sodium chloride and water byproducts. The answer is 29.54% atom economy. Problem 2. E-factor calculation. A pharmaceutical synthesis uses 5.0 kilograms of starting materials, 12.0 kilograms of solvents, 3.5 kilograms of reagents, and 25.0 kilograms of water. After workup, 0.85 kilograms of pure product is isolated. Calculate the E-factor. Step 1. Calculate total material input. 5.0 plus 12.0 plus 3.5 plus 25.0 equals 45.5 kilograms. Step 2. Product mass is 0.85 kilograms. Step 3. Waste equals total input minus product. 45.5 minus 0.85 equals 44.65 kilograms. Step 4. E-factor equals 44.65 divided by 0.85, giving 52.5. Step 5. Interpretation. 52.5 kilograms of waste per kilogram of product is typical for pharmaceutical manufacturing. Conclusion. Water and solvents contribute most to the waste stream. The answer is E-factor equals 52.5. Problem 3. Carbon efficiency. A reaction converts 2.0 moles of benzene into 1.5 moles of aniline. Calculate the carbon efficiency of this reaction. Step 1. Moles of carbon in benzene reactant. 2.0 moles times 6 carbons per mole equals 12.0 moles of carbon. Step 2. Moles of carbon in aniline product. 1.5 moles times 6 carbons per mole equals 9.0 moles of carbon. Step 3. Carbon efficiency equals 9.0 divided by 12.0 times 100%, giving 75%. Step 4. 25% of carbon is lost to byproducts or unreacted starting material. Step 5. If the reaction had 100% yield, carbon efficiency would be 100%, since all 6 carbon atoms are retained in aniline. Conclusion. The answer is 75% carbon efficiency. Problem 4. Reaction mass efficiency. In a reaction, 15.0 grams of reactant A with molecular weight 150 and 8.0 grams of reactant B with molecular weight 80 produce 10.5 grams of product C. Calculate the reaction mass efficiency. Step 1. Sum of all reactant masses. 15.0 plus 8.0 equals 23.0 grams. Step 2. Mass of isolated product is 10.5 grams. Step 3. RME equals 10.5 divided by 23.0 times 100%, giving 45.7%. Step 4. RME includes both yield and stoichiometric excess effects. Step 5. Compare with theoretical atom economy if the reaction went to completion with 100% yield. Conclusion. RME less than 100% indicates room for optimization. The answer is 45.7%. Problem 5. Process mass intensity. A process uses 2.0 kilograms of reactants, 8.0 kilograms of solvents, 15.0 kilograms of water for washing, 0.5 kilograms of catalyst, and 1.0 kilogram of workup reagents to produce 0.4 kilograms of product. Calculate the process mass intensity. Step 1. Sum all material inputs. 2.0 plus 8.0 plus 15.0 plus 0.5 plus 1.0 equals 26.5 kilograms. Step 2. Product mass.